So this is chapter 2 from our book by Kroenke and Auer. This chapter is all about SQL, SQL, the structured query language. But nobody calls it that, right? It's always SQL. What's the point of SQL? I tried to encapsulate it with this statement. The whole point of it is just to interact with a database. I know that's vague, and we're going to get more specific as we get into this. SQL allows users to ask questions of a database. That's going to be the focus of today's lecture. But it also allows users to define the structure of a database, to add, remove, and change data in the database, and even do some other, even more special stuff. All right, just a little bit of background on SQL. It was developed by IBM in the 70s, the late 70s. It was later endorsed and standardized by the American National Standards Institute in 1992. So you'll see a lot of people cite, as it were, SQL 92 as kind of one of the standardizations of SQL. And all of the major database products would support what's defined in this standard, but there's a bunch of other stuff that they may do as well that may be a little bit different from it and may differ from database product to database product. There are newer versions of it, but this is kind of the gold standard here. Note that SQL is not a programming language. It's not a programming language. It is not a full-featured language that can do the stuff that you're used to doing in a real programming language like C, C#, Java, Python, Objective-C, Swift. Does anybody want to throw one in that I missed? Okay, I didn't mean to leave that. JavaScript. Yeah. It's not a real language like that. It's a sub-language for creating and processing database data and data about data. So it's all about interacting with data and structure in a database. It's not about writing ifs and loops and those sorts of programming language statements that allow us to solve any problem, to implement any algorithm. This is in some sense, you could call SQL a domain-specific language. It's a special language that makes it easier to deal with problems in the data domain. It is a ubiquitous product used throughout enterprise-class database management systems, so everybody uses SQL. Even some of the languages that may have higher layers on top of it still use SQL. So like in the Microsoft stack, remember talking about LINQ, L-I-N-Q, which are language integrated queries. Those still are going to get, I think, mapped into SQL queries because that's what databases know how to understand is SQL. And SQL is very much a critical skill. This is super important. I just had a grad from last year, a May graduate, tell me he wished he'd learned more SQL stuff as he was applying for jobs. So this is important stuff to know, and I think no matter where you fall within that spectrum of knowledge worker, programmer, database administrator, right, kind of different levels of interaction that you're required to have with a database, you're going to need to know some SQL, and the more, really, the better. The book categorizes SQL into 5 different areas. These are sort of, you could imagine, different dialects of sort of the same language, this language that interacts with databases, that solve different problems. The first one that I'm going to mention is a data definition language. So SQL can be used for creating tables, creating relationships, and creating other structures within a database, like indexes and triggers and those other things we talked about. The DDL portion is just used to define this is a table. The table has these columns, those sorts of things. And this is the kind of language that has been written for us automatically when we use the MySQL Workbench. Remember how we've right-clicked and created stuff and used the user interface to make columns, and we said apply, and we saw a bit of SQL code. That would be this SQL DDL, this DDL part of SQL. defining the structure. Second piece that we're going to talk about today in great detail is the data manipulation language. So SQL is used for creating queries, or this DML language. I'm sorry, that's redundant. This data manipulation language is used to query the data and modify the data. So the four main operations would fall into this: the creating, retrieving, updating, deleting. That's manipulation. A third portion of the language is about controlling data, and this is statements in the language that are used to grant or revoke database permissions for users and groups. And this is covered generally in Chapter 9, and we probably won't deal with it a lot in this class. So this is about giving different users of the database different access, so that you may have read or write access to different tables. Does that make sense? So very much a permissions-oriented thing. There are two other portions of SQL that the author points out, this persistent stored modules. And this, to me, kind of goes above and beyond what SQL is about. And that's why I put the top three as colors. In this SQL persistent stored modules, this actually does add procedural programming capabilities to the language. So things like variables and control of flow statements, that's like ifs and whiles and that kind of core programming language stuff. This gets added into the language here so that you can do additional processing of data. And this is generally covered in Chapter 7 in our book. The last piece here is the transaction control language. These kinds of statements are used to mark transaction boundaries and control transaction behavior. A transaction is basically something that you want to happen, and it needs to happen in a very safe way so that the whole transaction happens or none of it happens. That makes sense? So if we're going to say we're going to do like a transfer between two banking accounts, then we need to make sure that we withdraw money from one person's account and deposit it in another person's account. If we do half of that and get interrupted, then we need to make sure that we undo that half. Follow me? Doing either half of that without the other is very bad. So transactions would control it and say you have to do both things. You can do neither of them, or you can do both, but you can't do one but not the other. That's a transaction. All right, so there's another language that would kind of go around on top of this first layer of all the D's, all those types of statements, to make sure that they happen in a safe way when there's concurrency involved, when there's lots of stuff happening at the same time. Questions on this? This is still sort of the boring background stuff. Like I said, today we're going to very much concentrate on the green, the data manipulation layer, and we're really just looking at a piece of it. And in later chapters, we will consider the orange and maybe the blue some. This is the schema for the database that's the example database for this chapter. And this will be helpful because all of the author's examples come from this database. So the three tables that he highlights are the retail order, order item, and SKU data tables. They have those columns, and you can see what the data types are. All of this data represents like retail transaction information based on items that are sold, and then stores ordering items and stores selling items to people. I think it's maybe a little bit easier to see the relationships between these tables when you can see a little bit of the data like so. So you see at the top there's the retail order, and that has the store number. But the primary key is order number. It has the store number, the zip code for the store, the order, month, year, and the total number of dollars there. Order items, you see, every order has a number. There's also, you see that order number can be repeated. It's in there multiple times because an order number may have multiple SKUs, multiple items. It has the quantity, price, and then the total price. That's what he's calling extended price there. And then at the bottom, there's the SKU data, which has information on specific items within the database. That makes sense. So that SKU number is the a code for an item. There's a description, the department, and who bought it. So this is the database that we'll keep coming back to in our examples. If you have your book, you're welcome to open it up to where this diagram is if you want to see it while we go through the examples. It might be helpful if it's hard to remember all of the connections. All right. What we're going to talk about for pretty much the rest of today is the select statement. The select statement is a statement that's used to get data, to ask a question and get an answer, to retrieve data. Perhaps there are other words we could use that are synonyms of get and retrieve. Right? That's what they do. Right. Here's the basic framework for a select statement. We're going to select, and we're going to have a list of column names. We'll have the keyword from, which has a list of table names. If we have multiple items, we separate them with commas. And then we may optionally have conditions that follow the where keyword. Okay. A couple things to throw in here. All SQL statements should end with a semicolon. Not all DBMSs enforce that rule the same way, so some might let you get away with it, but you really should just get in the habit of ending your SQL statements with a semicolon. And that feels good, right? As C++ people, right? As C-based language people, it just feels right. Have you ever caught yourself putting a semicolon at the end of an English sentence? That's when you know you're a real programmer. Another thing to note, white space doesn't matter. As in, you can put in, you have to put in one space to separate your words, but you can put in tabs, multiple spaces, and it doesn't matter to the execution of the statement. Also, case doesn't matter. So I could have written select in all lowercase and it would still be executed correctly by the database. But by convention in our book, and I think lots of database people write SQL keywords in all caps to really drive it home that this thing is a keyword. So let me show you some examples. And like I said, you can go back and look at these slides again if these things don't make sense. I understand this is going to be a lot to take in, but I believe in you. All right, this simple statement here, we're going to select department and buyer, so the comma-separated list of column names from the SKU data table. So can you imagine what the results are going to look like from this? We're going to get 2 columns, and we'll have as many rows as there are items in SKU data. Keynote. So here's an example of the kind of data that we would get back from that query from this sample data set. So this is a basic select where we were selecting all the rows, 2 columns, all the rows from this table. Questions on this? If we change the order to buyer, comma, department, then that will change the order that the columns are represented in the resulting data set within the rows that are returned. Does that make sense? So you see how now buyer is first because I asked for buyer first. We can also use the keyword distinct. And when we use the keyword distinct, we mean only get me unique, in this case, buyers. So because we said distinct buyer, comma, department, we get all of the individual buyers, and we don't get Cindy Lou repeated several times. Make sense? As the book points out, the downside to this is in order to determine if there are any duplicates and take them out, the database has to do some work. So if you had a table with millions and millions of rows, adding that one word could really slow down your performance. If it's, you don't do it unless it's necessary, probably. There's also this cool thing called a star. And when you say star, you get everything. You don't have to list out the individual column names. You get it all. So when we say select star from SKU data, we get all, 4 columns that are in that table. So the asterisk is a wildcard character when selecting columns. Questions up to this point? Okay, let's add in this where clause. The where clause allows us to filter rows. So we can search for specific rows from one table. The syntax that we use for this is we say where, some column name, condition. So the condition could be something simple like equals. And if we're doing equals on a string type of field, you have to use single quotes. These are air single quotes. It's important that you use single quotes, not the back quote. You know, back quote, it's on to the left of the 1 on your keyboard. Just make sure you don't ever use that for this. It has to be single quotes. So this then will return a result set like this, where the only rows that match are the ones that have water sports as the value in department. That makes sense? I feel like it's a pretty understandable, in terms of English, way of saying this. So give me everything from this table where department equals water sports. So it's not too far from how you'd say it if you were just trying to explain the idea of what you were doing. So that's good. We'll see in just a minute, maybe after this lecture, how we can write these queries and execute them in the MySQL workbench. And here's a slide that kind of gives you an overview of that. Mostly you're going to type stuff in and press the lightning bolt, and then it will do it and show you the resulting data set underneath. Let's keep going and keep looking at some more examples of basic SQL statements. So this is another example of the where statement, and that's going to filter rows based on some condition. So this is one of our basic example of a select statement. We're going to select columns from a table name given some criteria, some condition. Any questions on that? Okay, well, let's crank it up a notch. Now we're at the intermediate stage, and I'm just going to add on maybe just one more special thing here, the order by clause. So if we need our results to be sorted, we can very easily do that by just saying order by and listing columns, column names. So here's the example here. We're selecting star from order item and ordering them by order number and then by price. All right, so what that means is we're going to go from smallest to largest in ascending order based on order number. If there's a tie in order number, and if there are two order numbers that are the same, then we'll order by price next from lowest to highest. That's what this SQL statement tells the database to do. Does that make sense? All right, so if we wanted something to go in descending order instead of ascending order, what would we do? And there's another keyword, special keyword, DESC and ASC. ASC is default, ascending is default. But if we want to specify what order, we can do it by using the descending keyword there. You see how now the rows are in order descending by price. Okay, we can make conditions that are compound, meaning there are ands and ors. You understand that with your programming language background, what that means. So just simple, they're still fairly simple, simple to understand conditions that are compound. They can have multiple clauses. So in this case, right, we expect the department to be water sports and the buyer's name to be Nancy Myers. Likewise, we could say or, in this case, we'll accept department equals camping or department equals climbing. That makes sense what that would do there. So just some basic syntax, kind of stuff you'd expect to be able to do to make queries, to ask questions. Okay. Another possible tool you can use is the where in. In this case, you can list out a set of legal values, values that you care to catch. So in this case, we say where the buyer is in this list, and it's a list of items that are strings, so they have to be in single quotes. So this would be, you could do the same thing by saying buyer's name equals Nancy Myers, or buyer equals Cindy Lou, or buyer name equals Jerry Martin. You follow me? You could break this out into a bunch of ors. This is more concise, especially as that list gets longer. Yeah, that is the right picture on that one. You can also do the complement of that and say not in. So this will find anything not in this list. So it looks like Pete Hansen is the only one that matches in this case. If we want to sort of extend that idea to numbers, we can use between. So we can say this, I'm looking for an extended price between $100 and $200, presumably. And by doing that, we would get these. We can do a very equivalent thing by using the mathematical symbols greater than or equal, less than or equal, if you prefer to do that instead of writing between and. That's going to return the same data set. Sometimes we want to do a little bit, we want to do selection. We want to query using strings, and we want some more options like wildcard characters. And this is the way to do this in SQL. The underscore character matches exactly one character, and the percent character matches any set of one or more characters. All right, so underscore just matches one, percent means one or more characters, any character. So the way to use this is the like keyword, and then inside the statement, inside the condition, we're looking for anything that basically starts with the letters P-E-T-E. And the way I understand this, this does require a set of one or more characters, so it would require at least another character there. Just P-E-T-E, end quote, wouldn't match. Does this make sense as a wildcard character? Percent matches one or more characters. We know this is going to get Pete Hansen, one of our favorite buyers. We could put this percent on either side of tint, and then we'd find anything that has tint in the middle of it. This shouldn't be buyer like tint. It should be the SKU description like tint. Pretend like it says that. So you see we've got the two tints here in the description. I'm saying this shouldn't be buyer. It should be SKU description. Well, no, that's a good question. Maybe it does accept 0 characters, because I would think that would be more flexible anyway. Okay. That makes more sense to me after I think about it. The exact words that I read from the book and copied into this PowerPoint says 1 or more characters. I think it should be 0 or more characters. So let's go with that. We can test it and see how MySQL treats it. Yes. Yes. So the like is important in combination with these wildcards, because equals would just mean exactly equal to. And here's one more example where we're saying that something has a 2 preceded by some wildcard characters, and then it has, this is 2 underscores. You can't see it, but it is 2. So exactly 2 characters come after it. So since all our IDs are the same, all our SKUs are the same length, we're basically saying there's a 2 in the 3rd position. Not 4th position, sorry. You follow me? Because if there's 2 blank spaces after, it would have to mean there's a 2 in this kind of column of numbers. Does that make sense? So you can make sort of powerful queries, text-based queries using this. Any questions on this select where stuff? Okay. Next is these built-in functions. Often we want to do some analysis, some processing to the data that we're looking at. Oftentimes this data is numeric, so some of the basic functions that all people that deal with data may want to use are these 5. We want to count the number of items that the number of rows. We want to get the sum of the things in the rows. We want to average them, find the minimum, maximum value, and that's all these do. I feel like that's pretty straightforward. So the interesting thing is, the different thing here is, instead of simply getting a bunch of data back from the database, queries involving these built-in functions are going to aggregate or smush the data into one dimension, into one row. Does that make sense? So if I select the sum, parenthesis, of extended price, I'm going to say as order 3000 sum. If you say as, you're basically naming the column that you're going to get back, or kind of the variable that you're going to deal with. You can kind of think about it as a variable, but it's not exactly a variable because you can't manipulate it. You can only set this built-in function's result into order 3000 sum. But this is the table name, and we have this where clause where order number equals 3000. So we're finding all the order number 3000s and adding them up. And what we get is one row with one column. The name of that column is order 3000 sum, and the value in it is the sum of all of the rows that were in order 3000. Does that make sense? Questions on that? Are y'all really good, or you just don't want to say anything? That's fair. You do. So just to give you a little example of all of them, I'm going to select sum, average, min, and max from extended price. So this is over the whole thing. Before we did a where equals 3000. Now this is all of our orders. And we've named them something appropriate. So what we get back here is 4 columns, and they're all names that we've specified after the as keyword. And then the database has done the math for us, which is kind of nice. So it's added up the sum, the average, the min, and the max. Questions on this? Here's another built-in function that's really common. When you'd like to know how many things are in my database. For example, just how many rows are in my table. And you can do that by saying count star. I think you could put the name of a column in there, but you don't have to. If you really just want the count, it doesn't matter which column you choose because they're going to get the same. So count star will count all the rows in this case, order item, and return back just a simple integer, a number. There's 7 rows total is what this query means. We do count star. Now, if this isn't enough math for you, I've got more. SQL also lets you do basic arithmetic within your statements. So we can select quantity times price with that times keyword. Or it's not really a keyword, is it? I don't know. It's a key character. Is actually going to do the arithmetic, the multiplication, and we're saving it as EP. We're also getting extended price. So what this should be doing, extended price should be that value. Quantity times price. Right? So in this case, we're sort of checking it. So that the EP, extended price, should be equal to extended price. What's extended price is in the database. EP has been computed using this times in the query. That makes sense? You could do the other arithmetic operators just as easily. All right, so that's the end of the intermediate SQL section. Built-in functions, order by. Questions on those? Are you ready for more? Are you thirsty for more? You are, aren't you? Okay, let's take it up to advanced. You see what I've added on the end here are 2 more clauses, group by and having. Let me show you what these do. The group by operator allows us to do aggregation on sets of results. Before we saw that we could get back all the rows, or we could smush all the rows down into one to get the count over all the rows, the sum over all the rows, the average over all the rows. Yeah? What group by does is it lets us do a middle ground, which is add up some built-in function, some aggregate of sets of things. So in this case, we're selecting department, buyer, and count star, that's the count, and we're calling it department buyer SKU count from SKU data. We're grouping them by department, comma, buyer. So what we get from this is the sum of the number of times that we have Cindy Lou from camping. So that happens twice. It looks like they all happen twice. Jerry Martin and climbing happens twice. So we've smushed down those counts to just happening over department buyer combinations. Does that make sense? So we're not summing up we're not summing up the whole table, but we're summing up for every one of these combinations of department and buyer. When you say group by, I mean, so we can think behind the scenes. For one, we don't. I mean, the database is going to do it. We don't have to do it, but I would think that it would have to find out all the distinct department buyer combinations, and then count how many of them there are for every combination. This database apparently only has 4 combinations, which isn't. It's a small database, really small, just a toy database for us. Did that answer your question? So I mean, it has to kind of, the database would have to do the group by first before it can do the count. If it were implemented, I mean, if we were implemented, that's the way we do it. If we had it all, then it would just count the number of rows in SKU data. And it should be, I mean, it should be 8, right? Because we've got 4 twos. But this keeps it in those sets, and it won't aggregate any further than that. It groups the aggregation by that value. Does that make sense? We can combine group by with where and order by to get more complex queries. So in this example, we're doing the same count but by department, but we're not including the SKU of 302000. We group by department, so we're only counting by department, and we're ordering by department SKU count, which is this thing that we've created, the as keyword. So the count that we're counting, which is all of the SKUs per department, ignoring this SKU number, we're grouping by department, so these are the SKUs per department, because it's in the SKU data table. And then we order by our count, so it should go from the lowest count to the highest count, because we go ascending.
Not that it would make sense in this context, but you could say where SKU is less than greater than %.
And you could use the light operator, just like we saw before. Mm-hmm. But to do not equals, this is the way to do not equals. Okay, so you see how these are the results by department, the number of SKUs per department. And they're ordered by department SKU count, which is the thing that we computed, that the query computed. Yes? So let's take this up one more notch, and this is just about the end of the notches, kind of. What if we want to do conditional filtering based on an aggregated value? So what if I want to can have like a where clause for department SKU count. Does that make sense? So this thing that we've computed in our query, I actually want to filter it and say, I don't care about it. I don't want to see it unless there's more than one SKU count for department. Well, SQL won't let you do that with a where clause, but there is a special clause for it, and it's the having clause. So having, this is the way I think about it. This isn't what the book does it, but having lets you do where kind of things for a group by. Does that make sense? So it's sort of, because it's really like you're having to do that filtering at a different time in the process. Because, you know, when you do where, this where SKU is not equal to 302,000, that happens off the top, right? Those things go away and they're never counted inside any of this processing. After you do the processing of computing this count star, then we would, that's after we've done the aggregation that we check to see if the count is greater than 1. And if it is, then we order by. So this is a way of saying it's just like the previous query, but we're additionally filtering based on that count of the number of aggregated rows, the aggregated count. How much do you hate this, Ethan? It's up there? You don't even have words to describe. Okay, I know this is a lot to take in, but it's okay. We'll get through it. Just don't freak out. Okay, you're doing a good job of that. Okay.
In his defense, he's not allowed much sleep.
How much sleep did you get last night? The night before that?
No.
Are you doing this because you have to do homework or just because you're goofing off? Sorry. So this is sort of the end of the advanced section. Any questions on these advanced topics before we go on to really advanced? The last little portion of today's lecture is about how to do selects over multiple tables. And basically, there's two ways of doing it. Okay, there's two ways of doing a select that spans multiple tables. Most of what we've done today, all of it up to this point, has been one table. The first way of doing it is using a subquery. And the subquery, this is a pretty simple idea, is you have a select from where in, and you're selecting in another query, which looks a lot like this. It's another select from where. So it's like a query within a query. Are you feeling this? Because you know what's going to come next, don't you? We could have a query and a query and a query. Yes. I'll show you one of those in just a sec. The second thing that you can do, which is, I would think, is probably much more common, and we'll do a lot more of this, is called a join. And a join is a way to, hang on to yourself, join two tables together, combine two tables together, concatenate two tables together. Yeah? So let's look at subqueries first and then joins. All right, here's an example of a subquery. And I like to think about these from the inside out. So I'm going to select SKU, the SKU column, from SKU data, where department equals water sports. All right, so you see I've just got a bunch of SKUs that have water sports as the department. All right, that's my kind of inside data set. Then on that data set, I'm going to select the sum of extended price as revenue from order item, where the SKU is in this list of SKUs. So what is it that I've computed with this subquery? Think about that. In business words. All right, so you basically computed something for your boss, the manager, he's asked you a question, a business question, like how much revenue, what? Exactly. How much revenue have we had from water sport items? Yeah. So you see, it's a query within a query. Okay, can you hang with me one more slide on subqueries? You know what it's going to be, don't you? Do it? Okay, so now we have most inside query, a little bit outside, very outside, right? So we have you want to call it like a child and a parent and a grandparent query. So we're going to select order numbers where the month is January, the year is 2013. So those are the only orders that we're considering. And then we're selecting SKUs from order item where the order number is in here. Yeah. And then we're selecting the buyer from SKU data where the SKU is in this list. So can you imagine, can you kind of map out of this, what is the question that's being answered by this query? Somebody besides Alan, since he took the last one. Yeah, so we're trying to find the buyer, any buyers who made retail orders in January of 2013. And because our database is designed as it is, we've got to link all three tables together to answer that question. And this is the way to do it using subqueries. You see how these each are from a different table. This is from retail order, order item, and SKU data.
Can you do this kind of thing between tables if they don't have foreign keys?
No, I think this is a way that we're connecting those relationships. Okay, so this is subqueries. This is the kind of answer we would get. Questions on subqueries?
Yes. Do you go from like the nested rows to the outermost?
I would say you would go from the innermost to the outermost.
So it's not about selecting the
Hmm?
order from the retail order table, you select the order column and go to the revenue data and then step back to the order after table and select the SKU column and then check the revenue data and then step back again.
Yes. And that would be the efficient way of doing it. Otherwise, right, you'd like to get down to the fewest number of rows first before you start having to backtrack and see where all those rows connect to.
How do you get buyers in our results that didn't buy anything because we're taking the SKU numbers of items bought and then we're taking the names of buyers who bought items. So they might have bought an item with that SKU.
But you got to think about how you're doing it with rows in a table. Those rows that are here are only rows. These are orders, and we're tracing it back to SKUs in those rows, connected to those rows through a relationship, through a foreign key. And then we're tracing that back through a relationship to the buyer for those.
So the only SKUs from the order items you're going to have when you step down
Yeah. Does that make that? It kind of goes back to his question. Starting from the innermost and coming out. Good question. Let's talk about joins just a bit. I promise you we're close to the end. I only have 13 slides left, which might sound like a lot, but it's not. We got this. How do you join tables together? So basically, we want to connect two rows that have a connection from different tables together into one long row, one wide row. Potentially. Basically, this is a way of connecting data back together that is related to each other through a primary key, foreign key relationship. So in this case, we're saying select buyer and extended price from SKU data order item. We call that buyer. Buyer is from SKU data. No. So, no, both of these are from. Neither is from SKU data. So we're getting buyer and extended price from the two tables, SKU data and order item, where we tell it the where clause, we're saying this is the connection that the relationship between these two tables. SKU data.SKU is equal to order item.SKU. And this is the resulting data set that we would get from that. So this way of joining is a way of connecting data from different tables that have a primary key, foreign key relationship with each other, and making, sort of causing data that causing data to be replicated that wasn't. So you see we have Nancy Myers here a bunch of times and Cindy Lou here twice. That data didn't exist altogether in a duplicate way in our database, but the join connected it back together. Let me show you another example. More complex example. In this case, we're getting the buyer and the sum of the extended price. So this is the amount of money, the amount of revenue for every buyer. We are using these two tables. We're saying this is the join, this is the same thing, that same relationship that these two tables are connected on. We're going to group by buyer so we can aggregate these by buyer and order by buyer revenue descending. And so this shows us what each buyer bought, the total number of dollars that each buyer spent. If we had to connect 3 tables that were all connected through foreign key, primary key relationships like exists in our system, then our join statement, we'd have to have 2 conditions. We'd have to explain, in this case, that the SKU data.SKU is equal to order item.SKU, and the order item.order number equals the retail order.order number. So this is specifying out in syntax, in code, these are the relationships that exist between these 3 tables. We have 2 relationships between them. And by doing that, we can combine columns that exist in different tables into one data set. That's often something we want to do. Now, if we go back to the previous example, which was this is one way of doing joins. This is the way I learned to do joins, and this way makes sense to me. But there's an alternate syntax as well that maybe is better or more natural. And this is what it looks like. It's join on. So this is the exact same query. It's just a different syntax where I've said I'm still getting the same things. I'm getting it from SKU data, join, second table, order item, on, and then this is the condition that we're joining those 2 tables on. Does that make sense? So these are 2 equivalent queries. This one makes the join very clear that I'm joining 2 tables together on a specific condition. Who likes to join on better? Who likes the straight up where better? Thanks, Adrian. And who really despises both? Yeah, thanks, Spencer. Okay. Well, I think I messed this one up. This isn't the right subtitle. This isn't subqueries. This is an example of multiple joins. All right, so if we're going to join multiple tables together, as in 3, then we have to have we have to have two join statements, two join-ons, and that's all this is showing, I believe. And y'all trace that out? You'll note that if you have two columns with the same name at play, then you need to say table name dot column name, right? Because there's a retail order dot order number and another, isn't there another order number too? The order item. So you'd have to specify which one of those, or that you need to use those, when you need to use those, which table they come from. Joins allow us to pull together a bunch of different columns from different tables so that we can see kind of everything in one view, even though a lot of it is going to be kind of redundant, potentially redundant. Right. The last thing, I'm pretty sure this is the last thing, really, I mean it this time, that the book covers in this chapter is about types of joins. And the way the book did this is junk, all right? The way I do it, way better. I got this example from codinghorror.com. This is a really good example. All right, so these are our two tables we're going to work with. Table A and Table B. They just have 4 items in each, and we're going to see inner, outer, left, and right joins, okay? So these are different ways that we may need to combine, to join rows together from different tables. First, let's look at the inner join, because it's sort of perhaps the most famous, kind of the default way. Okay, so we've got table A and table B. Oh, to make that go away. The inner join is represented by this Venn diagram. So it's the things that match, things that are in both tables. So when we get joined together, this will be the result with an inner join. We just have Pirate and Ninja in our result set. Does that make sense? You see, it's like inside, it's within the two. Well, what if that's not what we want to do? What if we actually want to get all of everything combined together into one big list? Now, we can create a full outer join, and it looks like this. So a full outer join takes everything from both tables and squishes them together. You see that for several of them, like Monkey Spaghetti, Rutabaga, and Darth Vader, there's no matching record from the other side. And on a full outer join, we would just then, the database will return null for those items that don't exist in the other table. So in this case, the full outer join produces the set of all records in table A and table B with matching records from both sides when available, and when they're not available, it just gives nulls for both. Make sense? There's also something called a left outer join. And in the left outer join, we're going to get the complete set of records from table A with matching records when available from table B. If there's no match, the right side will contain null. See what's going on there?
If it's a one-to-many relationship, so we have one pirate and many pirates and B, how would that be?
I think it would have multiple rows for each one. I'm not 100%. We should test it. Good question. Let me ask you this. Not you, everyone. If we had a right outer join, what would it look like and what would be in our results? Yes. So it would be very much like the opposite of the thing we just saw. The right would have all this. Okay, one more. If we wanted something like this, or we just wanted the items that were in A and B, but not the overlap, we could do something like this. So this is how you could do this, just so that we have more Venn diagrams to look at. And let me just end with this. So I can't tell you, because I'm not a database guru, why you would need to use all of those different joins. What I can say is that it just depends on what you're doing. And there may be situations where you need to combine things in that way, in these different ways. Okay, and I can't just pull an example out of my hat right now and tell you why, but this is what people do. So I want you to know how to do it too, in case you need to do it. And I put this slide in here because I thought it was a nice summary of everything to show you how you could get all these different combinations from the Venn diagram of joins and inner joins, outer joins, left, right. All right, so as we conclude, what are the similarities in subqueries and joins? We just talked about both of them for a while. What's similar about them? Subqueries and joins both. Right, they both process multiple tables and kind of combine information in some way from different tables. Can you think of any differences? I don't know, I think that's too strong. You think? If there was no relationship, I mean, you're subquerying some other data set. And if those things aren't the same, then you shouldn't be, well, it seems like you shouldn't be filtering to in that data set. So I think there would be a relationship defined. That's right. The book's terminology is that basically the top table from the subquery is all that you're going to end up showing. Whereas a join, you can take multiple tables and there's no top and combine them all together. Okay, so let's sum up SQL. SQL is like the ring of power. It is the one database language to rule them all. I've tried to combine everything together. This is sort of what we learned today, except for joins. But select from where, group by, having order by. And I think they do need to be in that order, actually, if you're going to use them all. I think order by has to be at the end. Yeah. It's a lot to take in, but it's important stuff. And we're going to spend some time. I may have to give you several homework assignments to really help drive this home. So I appreciate you being here today and enduring this.